Hello there, and welcome to Video 7 of Module 4, the correlation coefficient and summary values. In this video, we'll be exploring the correlation coefficient, what it is and some of its properties and characteristics, as well as finding some summary values such as x bar, s sub x, y bar, s sub y, and slope and y-intercept of the least squares regression line, in addition to the correlation coefficient. At the end of the video, we'll also explore something called an influential point and how you can identify them. Let's get started. We'll begin with a definition. The correlation coefficient gives us an idea regarding the strength and direction of linearly related data. One of the problems with scatter plots is that if you change the scale of the axis that you're using, either the x-axis or the y-axis, you can distort the data so that it can be hard to tell if the data are linearly related, if they're positive or negative, and what the strength of the relationship is. So we're going to find a numerical value to summarize that information for us, and this value is going to be R. We're using R, I think, for correlation, right? So R for the R's in correlation. Before we talk about how you can find R, let's explore some of the properties and features of R so we understand what kind of information it tells us and what sorts of values we should be expecting to get when we look for R. So first, R is always between a -1 and a +1. So it's impossible to have a value for R that's bigger than 1, either positive or negative. The closer R is to either +1 or -1, so the closer the absolute value is, I guess, to 1, then the stronger the linear relationship. The closer the value of R is to 0, the weaker the linear relationship. So if I have an R value of, say, 0.85 or 0.9, that's going to be a pretty strong relationship because it's close to 1. If I have an R value of like -0.2 or 0.15, then that's going to be a very weak relationship because those values are closer to 0. If the R value exactly equals 1 or -1, then that would mean your data form a perfect line. When you plot the points, they are all exactly on the least squares regression line. This is very rare, by the way. That almost never happens with real-world data. Then, the sign of R, whether it's positive or negative, is going to tell you the direction of the relationship. So, if R is a positive 0.9, that means you have a strong positive relationship. The scatter plot is going to look like it's going uphill from left to right. If R is a negative number, so like -0.75, that would indicate a negative direction. So the points would be going downhill from left to right on the scatter plot. Unfortunately, R is not resistant to outliers. So in fact, we'll see an example today where we have some outliers and what impact it will have on R. Lastly, R is not appropriate to use if the data are not linear. So if my data form no shape, or maybe they form a parabola or some other kind of curve, then we cannot do linear correlation analysis with that data because it's not a line, it's not linear. So we can only use R if our data are linear. If it's not linear, there are other analyses that you can do, but for the purposes of this video series, we are only looking at linear data or nonlinear data. We're not going to explore nonlinear data in great depth. So to help us get a handle of what type of value of R we should get based on a visual representation, I have 4 scatter plots here. In the first scatter plot, we have a strong, negative, and linear correlation. So it's strong because those points are really close to forming a line. So it's linear because it's close to forming a line. And it's negative because it goes downhill as we move from left to right. For this sort of a graph, I would expect an R value to be close to -1, maybe -0.95 or -0.98, something that's very close to -1. It's going to be a negative value because the direction of the scatter plot is negative. In the second scatter plot on this page, we have a moderate, linear, and positive correlation. Positive because it's going uphill from left to right. Linear because these points kind of look like a really thick, fuzzy line. And moderate because it's much fuzzier than that first scatter plot, right? These points are much more spread out, but we can still see that there's a definite trend happening. In a situation like this one, I might expect R to be close to a positive 0.75. So a moderate correlation is generally in the high 0.70s or in the low 0.80s. Whereas for a strong correlation, it would be on the higher end of the 0.80s or throughout the 0.90s. Anything less than a 0.7 is not really moderate. That's not really too much of a correlation. So for a moderate correlation, such as in the second picture, I would anticipate something close to a 0.75. Again, it's positive because the direction of the points are positive as well. For a weak correlation, there's no direction and there's no shape because these points do not appear to be correlated whatsoever. So in that situation, I would expect an R value to be 0. If we were going to make a least squares regression line for this third scatter plot here, it would probably look like a horizontal line. That's what happens when R is close to 0 because there's no real relationship happening, so there's no real sense of prediction to make. And for the last picture, we have a strong relationship, but it is nonlinear. It's got that parabolic, that U sort of shape to it. So because the values are not linear, it is not appropriate to use R for this last scatter plot. I shouldn't be using it. It's not going to give me valuable information. So how do we find R? What's the formula? Well, it's this beautiful formula here where you take 1 away from your sample size, and then you have to find the sum of a product. So that's going to be fun. Remember when we found our standard deviation by hand before, we had a table for x minus x bar, and then x minus x bar squared. And we had to find a total for that last column, and then we could find the standard deviation after that. So for R, if I'm going to find this by hand, I'm going to need a column for x minus x bar, as well as x minus x bar over sx. Then I'm going to need the same thing for the y's, y minus y bar, and y minus y bar over sy. And then I'm going to have to multiply those two things together. And then I'm going to have to add all of those things up to get this giant summation here. And lastly, I would divide by 1 less than the sample size. So here's the secret. Nobody uses this formula by hand, so we're not going to. So your instructor, if it's not me, may require you to do a few examples of using this formula by hand, but I don't ask my students to do that. Instead, we're going to use either a calculator or perhaps Microsoft Excel to find this value for R. When we find R, we're always going to round it to 4 decimal places, unless we've been told to do otherwise. So that's the standard that I'm going to adopt moving forward, is that it's just assumed R is going to get rounded to the nearest 10,000th, so 4 decimal places. Now, depending on the technology that you have at hand, your methodology is going to be a little bit different from what I'm going to do in this video. I had to pick one for the video, so I decided to use Microsoft Excel. So I'm going to use Excel to find some summary values. You can use your statistical calculator to determine these values as well, and then you can check with my answers to see if you got the same values. It doesn't matter the tool we use, they should both give us the same answers. Before we begin to summarize the bivariate data, just a note that you should always assume the data comes from a sample unless you are specifically told that it comes from a population. That will never happen, really. So this is mostly going to impact the standard deviation because we have different formulas for a population standard deviation or a sample standard deviation. So we're going to need to use the formulas or the technological tools to find a sample standard deviation. So throughout Module 4 videos, we've been looking at a data set that concerns the displacement volume of an engine and the vehicle's combined city and highway gas mileage. So we're going to continue working with these values in this video. We're going to first find individual summary values. So we're going to find the mean for the displacement volume and the standard deviation for the displacement volume. We're also going to find the mean and standard deviation for the combined gas mileage. As I mentioned before, I'm going to use Microsoft Excel to do this, but you can use a statistical calculator and compare your results to the results that I find here to see if they match up. Okay, so the very first thing you're going to want to do, whether you're using Microsoft Excel or another spreadsheet program, or if you're using a statistical calculator, is to enter out all of your data, or enter your data in. So what I've chosen to do here is I've entered my X values into column A, and all of my Y values are in column B. Then I've also given myself some space to find the means and standard deviations and some other values. Now before I move on, I haven't typed them out earlier on the screen too much, so I did want to put them here. The notation that we're going to use for the mean of the X values is X bar, and the notation we're going to use for the mean of the Y values is Y bar. We've used this similar notation before for sample mean. What's different now is this Y bar, and it kind of makes sense because we have an X and we have a Y, so sample mean for X is still X bar, sample mean for Y is going to be Y bar. For standard deviation, I need to make sure I'm differentiating between the standard deviation for the X values and for the Y values. So we're going to use subscripts. So the standard deviation for our X values will be S with a subscript of X. The standard deviation for the Y values will be S with a subscript of Y. So with the notation down, let's find these four summary values. In Microsoft Excel, the function that finds a mean is just called average. So here into cell E2, I'm going to type equals average of A2 through A11 because my data is stored in cells A2 through A11 for my X values. When I hit enter, the value 2.64 appears. For the sample standard deviation, the function in Microsoft Excel to find a sample standard deviation is stdev.s. So into cell E3, I'm going to type equals stdev.s, and then in the parentheses, I type A2 to A11, again, because that's where my X values are stored. When I hit enter, the standard deviation will appear. We're going to do exactly the same functions for the Y bar and the SY. We're just now going to refer to column B instead of column A. So for the Y bar, I'm going to take equals average of B2 through B11, and that gives me a mean of 26.7. And then for the Y standard deviation, I'm again going to use stdev.s, and that will give me the standard deviation for the Y values. And here, that's about 4.19. Okay, so now that we have our summary values from Excel, let's return to what we were asked to find. We were asked to find these four values, and we were told to round them to certain places. We also have to remember to label our answers when we provide them. So the volume was being measured in liters, so for both the volume mean and volume standard deviation, I have to make sure I label my answers accordingly. Rounding 2.64 to the nearest tenth is going to give me an X bar of 2.6 liters. For the volume standard deviation, we need to round that to the nearest hundredth, so 2 decimal places. So that will round to 1.35 liters. For the mean mileage, this is now going to be measured in miles per gallon. So to the nearest whole mile per gallon, Y bar is going to round to 27 miles per gallon. And then the mileage standard deviation to the nearest hundredth, again to 2 decimal places, is going to be 4.19 miles per gallon. So these are the four summary values for our X values and for our Y values. Next, we're going to use Excel to find the slope, the y-intercept, and the new correlation coefficient for these data. So I'm back in my Excel spreadsheet. And what's really nice is that the functions for slope and y-intercept are really nicely named. The function to find the slope is going to be slope, and the function to find the y-intercept is going to be intercept. So this should be pretty easy to remember. However, remember back when we looked at the scatter plots for bivariate data, the formal name of the scatter plot is the y variable versus the x variable. So when we input bivariate data into Excel, so when we have an Excel function that requires us to reference both the x values and the y values, the standard it has adopted is to ask us to enter the y values first, followed by the x values, because we have y versus x. So y gets entered first, followed by x. I know this is confusing because when you graph a point, you do x first and then you do y, but Microsoft Excel does what Microsoft Excel does, so that's what we're going to be stuck with. So for the slope of the least squares regression line, I'm going to type in equals slope, and then I will enter B2 colon B11, because that's where my y values are stored. I'll type a comma for the second argument, and then type in A2 colon A11, because that's where my x values are stored. So this is how you can find the slope of the least squares regression line using Microsoft Excel. I hit enter, and it tells me negative 2.80416, blah, blah, blah. For the y-intercept, we're going to follow the same process, except now we use the function called intercept. So I type in equals intercept. I make sure I type in my reference for the y values first, and then I type in my reference for the x value second. I will hit enter, and I get 34.103,00533. For the r value, there's no equals r in Excel, but instead of having us type out correlation coefficient, they did take a little bit of mercy on us, and so we're going to type in correl. So it's an abbreviated form of correlation. So to find r in Excel, you type in equals CORREL, and then we'll follow the same habit of entering our y values first, followed by our x values. Now, in truth, if I'm being honest with you, it doesn't matter for the correlation function whether you do x or y first. You'll get the same answer either way. But it does matter for the slope and the y-intercept. So to help prevent a sloppy mistake when we need to be precise, it's best just to have a good habit of entering your y values first and then your x values into bivariate functions in Excel. When I hit enter, I get negative 0.906009617. Again, if you're using a technology other than Microsoft Excel, you can follow your calculator manual, etc., and see if you get the same values that I found here. As before, we want to summarize these values as we've been asked to report them. So the slope to the nearest thousandth is going to involve that negative 2.804168686 number. Remember that the slope units are units for y per units for x, meaning our units are going to be miles per gallon per liter. To the nearest thousandth, we end up with negative 2.804 miles per gallon per liter. For the y-intercept, again, we're going to round to the nearest thousandth, but the units for the y-intercept are just the same as the units for y. So, rounding to the nearest thousandth, I get 34.103 miles per gallon. Lastly, we have to report our value for r. The good news is that r does not have any label, so we just have to write the number here, in this case to the 10,000ths place. So I'm going to write negative 0.9060. So that's how we find these summary values in Excel. Okay, now we've been asked to write an equation of the least squares regression line. We can do this using the values we've just found. Remember, we found the slope to be negative 2.804 and the y-intercept to be 34.103. The form for the least squares regression line is y hat equals mx plus c. So I'm simply going to substitute in the values for m and for c, and I leave the variables y hat and x alone. So I get y hat equals negative 2.804x plus 34.103. So that's my answer, and I'm going to box it in. Now be very careful when you are asked to state an equation of the least squares regression line. Your answer doesn't really look like an answer. It's a formula. So whenever you see that phrase, write an equation, your answer should be an equation. It shouldn't just be a single number. A common mistake that I see to this is plugging in either x bar or y bar into the formula for the x and the y. You don't want to do that. You want to just leave the x and the y there because you need the variables in order to have the formula, in order to have the equation. So make sure you star this in your notes or something so you know that when it says write an equation, it means write an equation. Don't give me a number for an answer. Also, if you've been watching the videos throughout Module 4, you may recognize this as the formula that Harriet gave us earlier. She put the numbers in a different order. She said 34.103 minus 2.804x, but it's the same formula. You can commute numbers because addition has commutative property, so you can change the order if you write things. What's important here is that the slope is matched up with the x, and the y-intercept does not have a variable attached to it. Okay, so now we're going to do a little bit of an experiment since we now know how to find some summary values. So I just have this indescribable data set really, just some x and y values. We don't know what these are, what they represent, but I did make a scatter plot of them. And we can see that most of the data is pretty consistent and close to being a line, but there are a couple of points that seem pretty distant from the rest of the data set. So the first one that caught my eye was this point up here. If I look at the x value, it looks like it's just before 10, and the y value is just before 50. So comparing this point to my data in the table, this must be the point 848. This looks to me to be an outlier because it's pretty far away from the rest of the data. And it is really different from the data as well. This other point all the way to the right of the scatter plot is also kind of an outlier. It's far away from the rest of the values. In fact, its x value is almost double the second highest x value, right? The second highest x value is almost 20, and this one is almost 40. So this one looks like it's the point 3632. So remember I had mentioned earlier that R is not resistant to outliers. So we need to see if these 2 points, which I'm going to call the red point and the yellow point, we're going to see if these 2 points make a difference to R and to our least squares regression analysis. So I hopped into Microsoft Excel. I entered this data, this time into columns B and C, and I did 3 analyses. In the gray box, I found the R value, the slope, and the y-intercept for the full data set. So this includes both the red and the yellow points. Then in that little red box where it says without 848, I pretended like 848 wasn't there, and I found the summary values for that as well. And then I did the same thing for the yellow point, 3632. So I pretended that wasn't there, and I found the summary values. So if we compare them, we can see that for the full data set and without 3632, the value for R is really small. That's a very weak correlation. That's because these data sets are including that red point, which was like up towards the top of the screen, had no business being there. You can see if we get rid of that point, so if we got rid of 848, the correlation coefficient jumps up to 0.9760. That's a huge difference, right? So just that single point had such a giant impact on R. So If an outlier has a significant impact on your data, on your least squares regression line, we say that it's an influential point. Influential points are points that have high influence on the summary values. So let's look at those 2 points that we were examining before, 848 and 3632. To help us out, I've reproduced the summary values we found in Excel. To see if it's an influential point, you especially want to look at the slope and the y-intercept for the least squares regression line, as well as R, to see if the point made a big difference. So comparing the full data set with 848, we've already observed that R was a big difference, but also notice that the slope and the y-intercept of those 2 data sets are different. In the full data set, the slope was 0.37, and when we got rid of that point, the slope changed to 0.49. The y-intercept also changed by about 4 points. It changed from 18.5 to 14.7. So these are some pretty significant differences. So I would say yes, 848 is indeed an influential point for our data set. If I look at 3632, we're going to compare the values from the yellow column with the gray. So we're going to compare without 3632 to the full data set. Here, the R value is 0.2, which is still smaller than the full data set, which had an R value of 0.36. So the R value is a little different. I mean, it's not as different as the other point was, but it is a little bit different. The slope and the y-intercept, however, are really similar. The slope without 3632 was 0.36. It was just 0.01 away from the slope of the full data set. Similarly, the intercept is only off by a tenth. It went from 18.5 to 18.6. So the line, the least squares regression line, isn't actually going to change all that much. So we would say that 3632 is not an influential point because it didn't change the full data set values very much at all. When we look at the graph, we can kind of see why that would be happening. If I look at the yellow point, it's in line with where we might project those other dots to be. So that would make sense that the least squares regression line is not going to change much because of that point. However, if I look at the red point at the top of the scatter plot, that is going to distort my data. It's going to pull the least squares regression line up away from the bulk of my data and change things substantially. So that's why 848 is influential because it had a big, in this case, negative impact, and 3632 is not influential. The bummer is if your data set has influential points, you have to complete regression analysis both with and without them. So you need to do the regression, you need to find the y bar, x bar, sx, sy, r, the slope, and the intercept, and do all of that analysis twice for this particular data set. If both of these points had been influential, I might have to do it up to 4 times. Once for the full data set, once with the red dot but not the yellow, once with the yellow dot but not the red, and once without either one. So that would be a lot of more work if we were going to be analyzing this data set further. So you really want to make sure that when you're collecting data, you want to be as precise as possible. Potentially this red dot was a typo, but no one can really say. I mean, I don't know where this data came from. I don't even really know what it represents. So if you have influential points, you do have to do this analysis multiple times. All right, that concludes our video on summary values and the correlation coefficient. In the next video, we're going to use formulas to find the slope and y-intercept in case we don't have the raw data available to us. So, thanks for watching. Have a great day.